Okay, so today, first a small recap. In electrostatics, we found that we could expand V of r in powers of r and Pn of cos theta if we had a localized charge distribution. And this is called a multipole expansion. And the point is, of course, that if we're far away from the charge distribution compared to the size of the distribution, we could just neglect the higher order terms because they fall off as 1 over r to some large power. Now we're going to, well, maybe I should remind you that this is the equation for the scalar potential. As you can see, they're identical, except that these are 3 components, but each component separately fulfills the same equation as this one. Now it's tempting to think, shouldn't we have a multipole expansion for A as well? And of course there is. We can start off by looking at the following expression for A. As always, we draw the standard figure. As we can see, we integrate over the current distribution, which is now localized in space. We're looking at the vector potential at point P, the position given by r vector. This is the integral. As we can remember, we had the expansion for 1 over this vector thing here. I'm going to write that down. So I'm expanding this distance here from the point of integration to the point of the vector potential I'm interested in powers of this r here and the angle here. There you go. And of course we see that this 1 over r thingy here, we had that in the expression for the scalar potential as well. So we're going to take advantage of this here too. And let's see. The first few terms were the following. This is the monopole term. This is the dipole term. And this dot product gives us a cosine theta essentially. So that's where the Legendre polynomials kicks in. And then some more terms, of course. Well, infinitely many in principle. Now for the magnetic vector potential, as each component fulfills the same equation as V does, we're going to look at this expansion for one component at a time. And I'll do that as soon as I get some more space. So let's start off by writing down the expression for each component. The ith component of A couples to the ith component of J, naturally. Like this. Now I'm just going to start off by writing out the first few terms here. This is the monopole term. And I'm going to write down the dipole term. Looks just like the case for scalar potential and charge distribution, except now we're just looking at one component. And we can make some observations first on these terms. First of all, a monopole term, it will disappear. And this is because there's no magnetic charge. No one has ever found a magnetic charge particle. And intuitively, you could think of it like this. If you have some sort of localized charge distribution, say the size of a sponge, then if there's charge flowing in this direction, well, at some point it has to turn around and go in the other direction, right? Because there's no point, there's no source or sink of the current. It can't just disappear into a black hole, say. So for this reason, this term is going to be 0. And I'm going to make a small comment on that because just a few weeks ago there was someone who published a paper on a magnetic monopole quasi-particle. Do you know what a quasi-particle is? An example would be an electron hole, which I'm sure you heard of. So in a similar fashion, someone found something that looks and behaves like a magnetic monopole in some exotic materials. So if you find out that you want to work on that, you might have to add a term. But I wouldn't worry too much, because it's extremely, well, and no one has seen any real particles in, let's say, vacuum or a particle physics experiment on that. Okay, so for that reason the monopole term will disappear. I guess you can also show it mathematically, but I think physics is more important than mathematics. Now let's rewrite the dipole term, because that's going to be the first, most dominating term for this system. Let's see. Yep, there's an I here. It's small and not very clear, but it should be there. As I'm always looking at one component, right? But I could be looking at any of them. The expression would be the same. Let's see. I'll rewrite this as another integral. After all the cross products and so on, I take the ith component. Now let's see. This integral, I'm going to call it m. And that's the magnetic dipole moment. I just rewrote it to get it on a form which would sort of remind us of the dipole moment in electrostatics. And now, let's see, the half actually belongs here with the integral. So now, m like this. So I just calculate this integral. I find the magnetic dipole moment it looks much like the electric dipole moment, except now I got a cross product here. That's of course, well, in magnetic fields, these cross products show up everywhere. And I can just write down the dipole term. Because now I got the dipole moment and everything I need. Like this. That's the dominating term for, well, let's say if you have a magnetic dipole somewhere, let's say an atom with some excess spin, well then this is what it's going to look like when you're far away from that magnetic dipole. And just for comparison, I'm going to remind you what the dipole looks like in electrostatics. Like this, and the integral for the P, the magnetic dipole moment. So as you can see, they're mathematically quite similar to each other. Yeah. Let's see. I'm going to make a small, let's say, show you a special case result for the dipole moment. Let's say if you have a loop of current running around inside the plane. Let's say like this. I put some wire onto the blackboard. It's stuck to a plane. It's completely flat. It has an area A. There's a current I running through it, through the loop of wire, and I'm going to integrate. So I'm going to show you that in a second. Let's see. You remember the expression for m vector, I hope, because there's not enough room on the blackboard. But if it's in a plane and there's a wire carrying the current, it simplifies to the following. Like this. So I take a small dl vector, because that's where the current is, inside the length of wire, cross it by the position vector, like this, and then you got a small, well, then you got your integration function right there. Now I'll make the following observation. This area here, it's a tiny, tiny triangle of area ds. And I'm not sure if you remember, but you can always calculate that as a cross product, right? If you have a triangle with right angles in one corner, you could just do the cross product with two of the sides. So it's, let's see. Looks exactly like the thing up there. Now if I insert it, it just looks like I'm integrating all the little, let's say, surface elements. I'm just integrating to get the area of the loop. Like this. So in the special case that the loop is flat, you could just use this simple formula. You multiply the area by the current running through it. And if you're wondering what direction is this area, well, you just use the right-hand rule to find out the direction of m instead of wondering too much about the math. If the fingers follow the current, then the thumb will give you the magnetization, or the magnetic dipole moment. So if I'm far away from some small loop of current, this is what it's going to look like. Well, this is what the vector potential looks like, and this m is given by the simple formula. So it can also be used as to estimate roughly what's the dipole moment. And I'm going to make an example drawing to show you roughly what the field looks like. I'm putting the magnetic dipole moment along the z-axis, equivalent to putting the current inside the xy plane. These are my variables, phi, theta, and r. So the length of this is r. Well, you get that. And then the dipole looks like. So according to the right-hand rule, the vector potential points like this, same as the current. Yep. And the B field will look like this. There you go. It's of course orthogonal to the A because of the relation B equals nabla cross A. All right. Okay, so are there any questions to the magnetostatics chapter? Because I think this more or less finishes it. I'm going to make just a brief summary to gather all the ideas. And then if you have any questions, you can post them then. Okay, so let's just quickly repeat magnetostatics in 5 minutes. We have two fundamental equations, exactly as in electrostatics. First of all, there's no magnetic charge. And Ampere's law tells you the relation between H and current. And in vacuum, B is just proportional to H. So there's no real motivation to have H in vacuum, but as we get to materials, you'll see the point. Okay, we have the continuity equation for currents. which says that the charge is conserved, and indeed there's no time variation because we're in magnetostatics, right? So this is charge conservation in magnetostatics. If we have a distribution of current in space and there's a magnetic field in the area, it's going to be affected by a force that looks like this. So it acts like, you see the cross product? This stems from the Lorentz force law, right? You have, it's F equals Q V cross B. So if I'm moving with a charged particle in a magnetic field, well, then I'm going to get the right-hand rule for the force. It's orthogonal to the direction of motion. And this current is, of course, charged particles, so that's where this comes from. Of course, I need to get the B in the first place, and I do that by the Biot-Savart law. Which, as we remember, was an empirical measurement of how strong is the magnetic force for a certain current. It's the same as the Coulomb law for charges. It looks a bit like the Coulomb law as well, except there's this cross product which makes things a bit more complicated. We define our vector potential from the following formula. And one of the nice things about the vector potential was that when we wrote up this integral for that potential, we got rid of the cross product. And it also fulfills the Poisson equation, which we learned to solve in electrostatics. Because we learned it there, now we don't have to wonder what to do with A. Same thing. Also, we remember that we can select the gauge freely. And what does that mean? Well, I can change A as much as I want, as long as the B field stays the same. And of course, there's a lot of different A's that can give rise to, let's say, the same curl of A. That's the whole idea. And we'll get back to this more when we get time dependence and coupling. It will make it slightly more complicated, but this is the idea, and it's essential for what is called gauge transforms. It's important in cosmology and particle physics and quantum mechanics too. So even if you're not so interested in classical electromagnetics, this stuff is actually important for that stuff when you get to, well, even in quantum mechanics this stuff shows up, and it's quite useful. Well, necessary probably. Let's see. Yeah, we have the multipole expansion. The idea was to get some approximation to the vector potential at large distances. And hopefully it's enough to keep a few terms. That's the whole idea. If you have to keep a lot of terms, then this isn't working so well. And the first term is the dipole moment. And it's essentially the current times the area of a loop. Like this. Now there should be some sort of question, I hope. Anything in magnetostatics? Something that's not clear? right? The boundary conditions are of course important, but well, yeah. They should definitely be here, yep. So the vertical component of the B field is continuous. This was from the Gauss law, right? There's no magnetic charge. So for an electric field, there is charge. This is not continuous. There's a jump in the parallel component of H, because at the interface, if there's a current running, there's a discontinuity in the H field because of the Ampere law, essentially. There is a current term here, and of course, if there's a current nearby, it's going to affect the H field, and this is very pronounced at these interfaces. Also, the H is sort of material dependent. We'll get to that when we're done with this. And then you can also get discontinuities from the material properties. However, if you, for example, are interested in optics, there's not that many magnetic materials that are translucent. They're usually opaque. So if you're trying to look at a permanent magnet, you can't see through it. And for that reason, I mean, boundary conditions in electrostatics are actually they're good enough to start working on optics. Because in the electrostatic approximation, there's no time dependence, and you can see if I send it in a plane wave at an interface, or a different wave for that matter, what happens to the field at the interface. And then the epsilons, as we could see, they affect the optical properties. That's why electromagnetism is so essential to understand anything in optics. But as there are not so many magnetic windows, let's say, it's hard to make a magnetic lens. So there's not so important for optics, at least. But I'm sure you could find some example where you need this. Because there's so few materials that are strong magnets, which we'll discuss in a few minutes. Yeah, not quite as important, I'd say. Because many materials act more or less as a vacuum in terms of magnetics. Any other questions? Okay. Right, so let's skip to chapter 6, which is magnetic fields in matter. Basically, the magnetic phenomena are due to charges in motion, in some sense of the word. That's the essence of it. If there is a current running, or there could be an electron spin. Classically, you could look at it as a charge ball spinning around its axis, Quantum mechanically, this isn't entirely correct, but it shares many of the same properties as that. So those are sort of the sources of the magnetic fields. That's where they occur. And well, what typically happens in a material is that you look at tiny atoms or molecules, and if these are small, and well, we all know they are small, so we can look at them as magnetic dipoles. That's the approximation we're going to use. Typically, if I have a lot of these little magnetic dipoles on the microscale, they're not really oriented. So if I have, let's say, a piece of wood or plastic or whatever, there's no system to the little magnetizations. So if I have electron spins, or let's say I have an orbital with a spin in it, there's a magnetic moment associated, but there's no order to it. They're not aligned in any sense. Same as with electric dipole molecules, right? So if I have no external magnetic field, well, then there's no orientation. There's no magnetic effects in the material, at least on the macroscopic scale. However, if I apply a magnetic field to all these little dipoles, they're going to feel a torque exactly as we saw the electric dipoles feel a torque in an electric field. The same way the magnetic dipoles feel a torque in a magnetic field. For example, you can hold just two permanent magnets near each other, and you'll see that if you try to align them the other way, they'll try to get back, so to speak. They don't like being oriented the wrong way. You might not get complete orientation, but you will get some statistical effect at least, which means that you're going to see some macroscopic effect if you apply a large enough field. In fact, I've seen, I get to that, I think. Right. So if we neglect the complications of isotropic fields, and let's say anisotropic and nonlinear effects and so on, in general, in a dielectric, we typically get a polarization which is parallel to the E field. Now for, let's see, for electrostatics, that's a typical picture you get. But for magnetization, it's not quite so easy. In fact, we get three broad classes of materials, and the three are the following. The first one is called paramagnetic. The second is called diamagnetic, and the third one is called the ferromagnetic. And I think I'll put that over here because there won't be space. And for the paramagnetic case, the mechanism is very similar to this sketch. It's typically if you have the most typical case is if you have an odd number of electrons in the electron cloud surrounding an atom. There's one electron which has not formed, let's say, a pair with another one, aligning the spin in the opposite direction. This is essentially the Pauli principle, right? There's one free, well, the last, you fill up all the quantum numbers, and then the last electron doesn't have a partner, so it actually has a spin that you can align. This is typically for a paramagnetic So the spin typically aligns along the H field, and let's see, the spin, that's the magnetization. And examples, let's say the result of this is, of course, as they align parallel, then the magnetic field is parallel too. So the local magnetization, which we'll discuss, is essentially the same as the polarization, is parallel to the applied external field. And examples is, let's say, molecular oxygen, aluminum, and platinum. There are several examples in the book as well. So that's a paramagnetic case.
Can you magnetize a gas? Or do you mean in solid state?
Yeah, but this is quite weakly. We'll get to the numbers, but it's not so much. So that's why if you have a magnet, the gas is going to feel some sort of interaction, but it's going to be weak, so you're not going to see it on the macroscopic scale unless you're very, 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 very careful. We'll get to that. In the diamagnetic case, however, the mechanism is different. You actually modify the orbitals of the atoms, of the electrons inside the atom. So if you have an electron cloud which did not originally possess a dipole moment, you get one from applying the external field. This is exactly the same as we saw in the electric case, right? You have an electron cloud, and then you start pulling the nucleus in one direction and the electron cloud in the other, and you induce a polarization from the applied field. And this is exactly the same, except in the magnetic case. So you modify the electron orbitals. There's a classical sketch in Griffiths. It goes something like this. It's not entirely correct, of course, because the effect is quantum mechanical, but it gives basically the idea. You have a big nucleus, or not big, but a heavy nucleus in the center of the atom. And you have some E- orbiting around in a radius and at a velocity. And if you apply a magnetic field now, then, well, I'm sure you calculated the radius of a charged particle moving in a magnetic field, right? So in addition to the electrical pull of the nucleus, you're either going to get an outwards or inwards pull from the magnetic field. This means that for a given radius, you could actually have a smaller or larger velocity. So you'll get a slightly different result if you're spinning the one way or the other way. And this will generate a small, very small magnetic dipole from the, well, if you want to calculate this for real, you have to go to quantum mechanics, of course, and higher order perturbation theory, I think. I haven't seen exactly how you do it, but that's where you need to go if you want to calculate it from first principles. Okay, and the result is that magnetization is now the opposite direction of the H field. Like this. And some examples. There's gold and silver and water. And again, this is very weak, so if you hold a magnet to the tap of water, you're not going to see anything. Like, while for electrostatics, the water is very easily polarized. It actually has a dipole moment, right? So if you pull a comb through your hair, you charge it up a bit, and then you hold it next to the water tap, you can see the water bending. I'm sure you've done that at some point, right? But you can't do that with a magnet. And we'll get to the numbers to explain that. The ferromagnets are basically similar to the paramagnetic materials in that you have an intrinsic dipole moment in the material. You just start to align it when you apply an external field. That's the basic mechanism. And the result is again that the magnetization points in the same direction as the edge field or the applied external field. But this is a very strong effect. And it's also a nonlinear effect because the alignment is actually so efficient that at some point you align all the dipoles. And then there's nothing more to align, and then it can't be linear anymore, right? Because if you double the field, there's nothing more to align, so there's no more magnetization. So it's a very strong and non-linear effect. This can be used, for example, to amplify the magnetic field. If you have a coil of wire, you put an iron core in the middle, you get a much stronger magnet, and that's from you get this extra help from aligning the microscopic dipoles. Another cause for the non-linearity is that if I turn off the current again, right? I have a rod of metal like a nail. I put a current through a wire looped around it, I get some magnetization. If I turn the current off, the magnetization might not be gone. Depends a bit on the material, but in principle it's not at least completely gone. So if you have let's say a screwdriver, you might see that it becomes magnetic at some point. If you put a screwdriver down here, put a current, it might be magnetic. This is convenient, right? Because you put the screw on the tip and you don't have to fiddle with two hands. Yeah. So this is also a cause for nonlinearity because when H equals 0, M might not be 0. Okay. And now to get to sort of rank these. The diamagnetic materials are very weakly magnetic. You can't see any effect unless you're really careful. The paramagnetic are also weak, but they're typically somewhat stronger. So the effect is a bit more. It's easier to measure, but it's still not easy to measure. I mean, if you're a kid playing around with magnets, you're never going to see anything. You have to be careful. But for ferromagnets, I'm sure you all know that. Well, as one of my lecturers said, if you didn't play with magnets when you're a kid, you don't belong here. I'm not sure if that's true, but I'm sure most of you played with magnets, and then you know that you can really see the quite strong effects. I bought this. There's a web page called powermagnetstore.com. They sell these really nice magnets. I bought just like 10 of them, and if you have 2 of them, you can actually put a book on your fridge. So this is much stronger than as someone commented, the magnetization of oxygen gas in the air. Okay. Let's see. Yeah, ferromagnetism and paramagnetism only occur when there's some sort of spin or a magnetic moment to align. While the diamagnetism actually occurs in all materials. It's just that it's weak, so if there's a ferromagnet or a paramagnet around, you're not going to see the diamagnetic properties just because it's the weakest, but it's always there. While for the paramagnetic and the ferromagnetic, it depends on, well, the material needs to have some properties. You need to have a dipole moment to actually align. Okay, so enough talk. There's some equations to look at. I think we take a break and then we start having some more fun.